Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics. 3 volumes in 1. By Isaac Asimov. Read by JohnLothe. Chapter 4. Gravitation. Combination of forces. Newton had already turned his attention to an important and very profound question while still in his 20s. Did the laws of motion apply only to the Earth and its environs, or did they apply to the heavenly bodies as well? The question first occurred to him on his mother's farm, when he saw an apple fall from a tree, and began to wonder whether the moon was in the grip of the same forces as the apple was. Footnote: it did not hit him on the head, despite the hundreds of cartoons drawn by hundreds of cartoonists. It might seem at first thought that the moon could not be in the grip of the same force as the apple, since the apple fell to earth and the moon did not. Surely, if the same force applied to both, the same acceleration would affect both, and therefore both would fall. However, this is an oversimplification. What if the moon is indeed in the grip of the same force as the apple, and therefore moving downward toward the earth? In addition, what if the moon also undergoes a second motion? What if it is the combination of 2 motions that keeps the moon circling the earth and never quite falling all the way? This notion of an overall motion being made up of 2 or more component motions in different directions was by no means an easy concept for scientists to accept. When Nicholas Copernicus, 1473 to 1543, first suggested that the earth moved about the sun, rather than vice versa, some of the most vehement objections were to the effect that if the earth rotated on its axis, and, still worse, moved through space in a revolution about the sun, it would be impossible for anything movable to remain fixed to the earth's surface. Anyone who leaped up in the air would come down many yards away, since the earth beneath him would have moved while he was in the air. Those arguing in this manner felt that this point was so obvious as to be unanswerable. Those who accepted the Copernican notion of the motion of the earth had to argue that it was indeed possible for an object to possess 2 motions at once, that a leaping man, while moving up and down, could also move with the turning earth, and therefore come down on the same spot from which he leaped upward. Galileo pointed out that an object dropped from the top of the mass of a moving ship fell to a point at the base of the mass. The ship did not move out from under the falling object and cause it to fall into the sea. The falling object, while moving downward, must also have participated in the ship's horizontal motion. Galileo did not actually try this, but he proposed it as what is today called a thought experiment. Even though it was proposed only in thought, it was utterly convincing. Ships had sailed the sea for thousands of years, and objects must have been dropped from mast tops during all those years, yet no seaman had ever reported that the ship had moved out from under the falling object. And of course, we can flip coins on board speeding jets these days and catch them as they come down without moving our hand. The coin participates in the motion of the jet even while also moving up and down. Why then did some scholars of the 16th and 17th centuries feel so sure that objects could not possess 2 different motions simultaneously? Apparently it was because they still possessed the Greek habit of reasoning from what seemed valid basic assumptions, and did not always feel it necessary to check their conclusions against the real universe. For instance, the scholars of the 16th century reasoned that a projectile fired from a cannon or a catapult was potentially subject to motions resulting from two causes. First, the impulse given by the cannon or catapult, and secondly, its natural motion toward the ground. Assuming, to begin with, that an object could not possess two motions simultaneously, it would seem necessary that one motion be completed before the second began. In other words, it was felt that the cannonball would travel in a straight line in whatever direction the cannon pointed until the impulse of the gunpowder explosion was used up. It would then at once fall downward in a straight line. Galileo maintained something quite different. To be sure, the projectile traveled onward in the direction in which it left the cannon. What's more, it did so at constant velocity, for the force of the gunpowder explosion was exerted once and no more. Without a continuous force, there would be no continuous acceleration, Newton later explained. In addition, however, the cannonball began dropping as soon as it left the cannon's mouth, in accordance with the laws of falling bodies, whereby its velocity downward increased with a constant acceleration, thanks to the continuous presence of a constant force of gravity. It was easy to show by geometric methods that an object that moved in one direction at a constant speed and in another at a speed that increased in direct proportion with time would follow the path of a curve called a parabola. Galileo also showed that a cannonball would have the greatest range if the cannon were pointed upward at an angle of 45 degrees to the ground. A cannon pointed at a certain angle would deliver a cannonball to one place if the early view of the cannonball's motions were correct, and to quite another place if Galileo's views were correct. It was not difficult to show that it was Galileo who was correct. Indeed, the gunners of the time may not have dabbled much in theory, but they had long aimed their weapons in such a way as to take advantage of a parabolic motion of the cannonball. Footnote: the correct aim, especially nowadays when shells are hurled for miles, requires more than the idealized parabola of Galileo. Many factors of the real world, as for instance the curvature of the Earth's surface, the manner in which its speed of rotation varies with latitude, the amount of air resistance, which varies with height and temperature, the strength and direction of the wind, the motion of the object aimed at and the object carrying the cannonball, if both are ships, for instance, affect the situation. All these effects merely serve to modify the parabola, however, and do not affect the basic worth of Galileo's argument, which serves only to present a greatly simplified but nevertheless vastly useful model of the real situation. In short, the possibility of a body's possessing two or more motions at once was never questioned after the time of Galileo. How can separate motions be added together and a resultant motion obtained? This can be done by vector addition, according to a method most easily presented in geometric form. Consider two motions in separate directions, the two directions at an angle, alpha, to each other. The symbol alpha is the Greek letter alpha. Greek letters are often used in physics as symbols in order to ease the overload of ordinary letters of the alphabet. The two motions can then be represented by two arrows set at angle alpha, the two arrows having lengths in proportion to the two velocities. If the velocity of one is twice that of the other, then its corresponding arrow is twice as long. If the two arrows are made the sides of a parallelogram, The resultant motion built up out of the two component motions is represented by the diagonal of the parallelogram, the one that lies in a direction intermediate between those of the two components. Given the values of the two velocities and the angle between them, it is possible to calculate the size and direction of the resultant velocity, even without the geometric construction, although the latter is always useful to lend visual aid. For instance, if one velocity is 3 meters per second in one direction, and the other is 4 meters per second in a direction at right angles to the first, then the resultant velocity is 5 meters per second in a direction that makes an angle of just under 37 degrees, with the larger component, and just over 53 degrees with the smaller. In the same way, a particular velocity can be separated into two component velocities. The particular velocity is made the diagonal of a parallelogram, and the adjacent sides of the parallelogram represent the component velocities. This can be done in an infinite number of ways, since the line representing a velocity or force can be made the diagonal of an infinite number of parallelograms. As a matter of convenience, however, a velocity is divided into components that are at right angles to each other. The parallelogram is then a rectangle. This device of using a parallelogram can be employed for the combination or resolution of any vector quantity. It is very frequently used for forces, as a matter of fact, so one usually speaks of this device as involving a parallelogram of force. The motion of the moon. Now let us return to the moon. It travels about the Earth in an elliptical orbit. The ellipse it describes in its revolution about the Earth is not very far removed from a circle, however. The moon travels in this orbit with a speed that is almost constant. Although the moon's speed is approximately constant, its velocity certainly is not. Since it travels in a curved path, its direction of motion changes at every instant, and therefore, so does its velocity. To say that the moon is continually changing its velocity is, of course, to say that it is subject to a continuing acceleration. If the moon is viewed as traveling at a constant speed along a uniformly circular path, which is at least approximately true, it can be considered to be changing its direction of motion by precisely the same amount in each successive unit of time. It is therefore undergoing a constant acceleration and must be subject to a constant force, according to Newton's second law of motion. Since the shift in the direction of motion is always toward the Earth, the acceleration, and therefore the force, must be directed toward the Earth. Certainly, if there is a force attracting the moon to the Earth, it might well be the same as the force attracting the apple to the Earth. However, if that were so, and the moon were undergoing a constant acceleration toward the Earth under the pull of a constant force, why does it not fall to the Earth as an apple would? We can see why if we break the moon's motion into two component motions at mutual right angles. One of the components can be drawn as an arrow pointing toward the Earth along a radius of the moon's circular orbit. This represents the motion in response to the force attracting the moon to the Earth. The other component is drawn at right angles to the first, and is therefore tangent to the circle of the moon's orbit. This tangential motion represents that which the moon would experience if there were no force attracting it to the Earth. The actual motion lies between the two, and the tangential component carries the moon to one side just far enough in a unit of time to make up for the motion toward the Earth in that same unit of time. The moon, in other words, is always falling toward the Earth, but it also sidesteps. In a sense, this sidestep means that the Earth's surface curves away from the moon just as fast as the moon approaches by falling, and the distance between Earth and moon remains the same. This can be made plain if one supposes a projectile fired horizontally from a mountaintop on Earth with greater and greater velocity. The greater the velocity, the farther the projectile travels before striking the ground. The farther it travels, the more the surface of the spherical Earth curves away from it, thus adding to the distance the projectile covers. Finally, if the projectile is shot forward with sufficient velocity, its rate of fall just matches the rate at which the Earth's surface curves away, and the projectile remains in orbit. It is in this fashion that satellites are placed in orbit, and it is in this fashion that the moon remains in orbit. In considering the moon's motion, therefore, we need only consider that component which is directed toward the Earth, and we can ask ourselves whether that component is the result of the same force that attracts the apple. Let's first concentrate on the apple and see how to interpret the force between it and the Earth in the light of the laws of motion. In the first place, all apples fall with the same acceleration, regardless of how massive they are. But if one apple has twice the mass of a second apple, yet falls at the same acceleration, the first apple must be subjected to twice the force. According to the second law of motion, the force attracting the apple to the Earth, often spoke of as the weight of the apple, must be proportional to the mass of the apple. But according to the third law of motion, whenever one body exerts a force on a second, the second is exerting an equal and opposite force on the first. This means that if the Earth attracts the apple with a certain downward force, the apple attracts the Earth with an equal upward force. That seems odd. How can a tiny apple exert a force equal to that exerted by the tremendous Earth? If it did, one would expect the apple to attract other objects as the Earth does. And the apple most certainly does not. The logical way to explain this is to suppose that the attractive force between apple and Earth depends not only on the mass of the apple, but on the mass of the Earth as well. It cannot depend on the sum of the masses, for when the mass of the apple is doubled, the sum of the mass of the apple and the Earth remains just about the same as before, and yet the force of attraction doubles. Instead, it must depend upon the product of the masses. If we multiply the masses, the small mass has just as much effect on the final product as the large one. Thus, the minute quantity, A, multiplied by the tremendous quantity, B, yields the product, A times B. If A is now doubled, it becomes equal to 2A. If that is multiplied by B, the product is 2A times B. Thus, doubling one of two factors in a multiplication, however small that factor may be, doubles the product, and doubling the mass of the apple doubles the size of the force between the apple and the Earth. Furthermore, the apple does not measurably attract any other object of ordinary size because the product of the masses of two ordinary objects is an infinitesimal fraction of the product of the mass of either object and that of the vast Earth. The attractive force between two objects of ordinary size is correspondingly smaller, and while the force does exist, it is far too small to be noticed in the ordinary course of events. Since the Earth attracts all material objects to itself, even the gaseous atmosphere is held firmly to the planet through gravitational force. It would seem that the force is produced by mass in whatever form the latter occurs. In that case, the Earth need not be involved. Any two masses ought to interact gravitationally, and if we notice the force only when the Earth is involved, that is only because the Earth itself is the only body in our neighborhood massive enough to produce a gravitational force sufficient to obtrude itself on our notice. Such is the essence of Newton's contribution. He did not discover the law of gravity merely in the sense that all earthly objects are attracted to the Earth. This limited concept is at least as old as Aristotle, and the word gravity was used in that sense for many centuries before Newton. What Newton pointed out was that all masses attracted all other masses, so that the Earth's attraction was not unique. Because Newton maintained that there was a gravitational attraction between any two material bodies in the universe, his generalization is called the law of universal gravitation. The adjective universal is the most important word of the phrase. Footnote: it is possible to contrive an exception. If the Earth were hollow, there would be no net gravitational force within the hollow. A body within the hollow would not be attracted by the Earth. However, this is a highly artificial exception that has no practical significance, for any body that is large enough to have an important gravitational field is too large to support a hollow structure. If this were all, we would now be able to decide the size of that component of the moon's motion that is directed toward the Earth. All bodies on Earth fall with the same acceleration, and therefore it might be decided that the moon, if it were in the grip of the same force, ought to do the same. In 1 second, it ought to fall some 4.9 meters toward the Earth. Actually, the earthward component of the moon's motion is much smaller than that. To account for this, one might suppose that the Earth's gravitational force weakens with distance, and certainly this seems a reasonable supposition. It is common experience that many things weaken with distance. Such is the case with light and sound, to name two common phenomena with which man has always been familiar. And yet is such weakening supported by experimental evidence? At first blush it might seem that it wasn't. A stone dropped from a height of 100 meters falls with an acceleration of 9.8 meters per second squared, and one dropped from a height of 200 meters falls with the same acceleration. If the gravitational force decreased with distance from the Earth, ought not the fall from a greater height involve a smaller acceleration? In fact, ought not the acceleration increase steadily as the stone approached the Earth, instead of remaining constant as it does? But Newton's view was that all bodies attracted all other bodies. A falling rock is attracted not only by the portion of the Earth making up the surface immediately under it, but also by the portions deep underneath, all the way to the center and beyond, to the antipodes, 12,740 kilometers, 8,000 miles distant. It should also be attracted by portions at all distances to the north, east, south, west, and points in between. It would seem reasonable that for a body like the Earth, which has nearly the symmetrical shape of a sphere, we could simplify matters. The pull from the north would balance the pull from the south. The pull from the west would balance the pull from the east. The distant pull of the antipodes would balance the nearby pull of the surface directly beneath. In consequence, we might suppose that the net effect is that the overall pull of the Earth would be concentrated exactly at its center. Footnote: it is so easy to say it would seem reasonable, and end with a happy conclusion that the gravitational force of the Earth seems to originate at its center. Yet it took the transcendent genius of Newton 18 years to convince himself of this fact, and he had to invent that branch of mathematics now known as the calculus before he could prove it to his own satisfaction and that of others. Throughout this book, I say it would seem reasonable, and it is clear, and it is easy to see, when I am reaching conclusions that in actual fact were attained only through great ingenuity and hard labor. In doing so, my conscience hurts, but in an introductory book I have no alternative. The radius of the Earth is about 6,370 kilometers, or 3,960 miles. An object falling from a height of 100 meters, 0.1 kilometers, begins its fall, therefore, from a point 6,370.1 kilometers from the Earth's center, while one falling from a height of 200 meters begins its fall from a point 6,370.2 kilometers from the center. The difference is so insignificant that the gravitational attraction can be considered constant over that small distance. Actually, modern instruments can measure the difference in the strength of the gravitational field over even such small distances with considerable accuracy. However, the Moon's distance from the Earth, center to center, is, on the average, 384,500 kilometers, or 239,000 miles. This is 60.3 times as far from the Earth's center as is an object on the Earth's surface. With a 60-fold increase in distance, gravitational force might indeed decrease considerably. But how much is considerably? The Earth attracts bodies on every portion of its surface. Therefore, the gravitational force may be considered as radiating outward from the Earth in all directions. If the force does this, it can be viewed as occupying the surface of a sphere that is inflating to a larger and larger size as it recedes from the Earth. If a fixed amount of gravitational force is stretched out over the surface of such a growing sphere, then the intensity of the force at a given spot on the surface ought to decrease as the total surface area grows larger. From solid geometry, it is known that the surface area of a sphere is directly proportional to the square of its radius. If one sphere has 3 times the radius of another, it has 9 times the surface area. As distance between two bodies increases, then the gravitational force between them ought to be inversely proportional to the square of that distance. This relationship is familiarly known as the inverse square law. Not only gravitation, but also such phenomena as the intensity of light, the intensity of magnetic attraction, and the intensity of electrostatic attraction weaken as the square of the distance. In comparing the motion of the Moon to the motion of an apple on the Earth's surface, we must remember that the Moon is 60.3 times as far from the Earth's center as the apple is, and that the gravitational force on the Moon is weaker by a factor of 60.3 times 60.3, or 3,636. Whereas an apple falls 4.9 meters in the first second of fall, the Moon should fall 1/3,636 that distance, or 0.0013 meters in a second of fall. A thousandth of a meter is a millimeter, so that 0.0013 meters is equal to 1.3 millimeters. Indeed, astronomical measurements show that the Moon in its course about the Earth does indeed deviate from a straight line course by about 1.3 millimeters in 1 second. This alone would have been sufficient to make it strongly probable that the same force that held the apple held the Moon. However, Newton went on to show how gravitational force on a universal scale would account for the fact that the orbit of the Moon about the Earth in an ellipse with the Earth at one focus, that the planets revolved about the Sun in a similar elliptical manner, that the tides took place as they did, that the precession of equinoxes took place, and so on. The one simple and straightforward generalization explained so much that it had to be triumphantly accepted by the scientific community. A century after Newton's death, the German-English astronomer William Herschel, 1738 to 1822, discovered instances of far-distant stars that revolved about each other in strict accordance with Newton's law of universal gravitation, which thus seemed universal indeed. Unseen planets were eventually discovered through the tiny gravitational effects produced by their otherwise unsuspected presence. It is no wonder that Newton's working out of the law of universal gravitation is often considered as the greatest single discovery in the history of science. Footnote. Nevertheless, Newton's generalization concerning gravity is only an approximation and is not absolutely correct. Already in the mid-19th century, it was discovered that the planet Mercury had one small component of its motion that could not be explained by Newton's law. It remained unexplained until Albert Einstein advanced his general theory of relativity in 1915. This theory, more advanced, powerful, and controversial than the special theory of 1905, involved a broader view of the universe than was implicit in Newton's laws. In all ordinary cases, the two views were just about equivalent at certain extremes. However, the two views diverge, and when such extremes are tested, it appears that Einstein's view, rather than Newton's, carries the day. The gravitational constant. Newton succeeded in establishing the generalization that any two bodies in the universe attract each other with a force, F, that is directly proportional to the product of the masses, m, and m hyphen, of the bodies, and inversely proportional to the square of the distance, d, between them. To convert the proportionality to an equality, it is necessary, of course, to introduce a constant. The one introduced in this case is usually referred to as the gravitational constant and is symbolized as g. Newton's law of universal gravitation can then be expressed as force equals gravity times mass of the bodies divided by distance squared. Equation 4-1. One problem left unsolved by Newton was the value of g. To see why it was left unsolved, let's consider the famous case of Newton's falling apple and try to substitute values in equation 4-1 in the MKS system of units. We know the value of the distance from the apple to the Earth's center and can set d equal to 6,370,000 meters. There are ways of measuring the mass of the apple, and m can be set at, let us say, 0.1 kilograms. As for the strength of the gravitational force, F, between the apple and the Earth, it is equal, see equation 3-3, to the product of the mass of the apple and the acceleration to which it is subjected by the action of gravity, according to Newton's second law of motion. The value of F, then, is 0.1 kilograms times 9.8 meters per second squared, or 0.98 kilogram meters per second squared. This leaves us with two items still undetermined: g, the gravitational constant, and m hyphen, the mass of the Earth. If we knew either one, we could calculate the other at once. But Newton knew neither, nor did anyone else in his time. You might wonder whether we could not eliminate the constant in equation 4-1, as we did the constant in equation 3-3. That, however, was done by a proper choice of units. We could do so here by inventing a unit called Earth unit, for example, and saying that the Earth had a mass of 1 Earth unit. We could further invent similar arbitrary units for the mass of the apple and the distance of the apple from the center of the Earth. Such tricks would be of limited value, however. It is unsatisfying to be told that the Earth has a mass of 1 Earth unit, and that is all we would find out in this way. What we want is the mass of the Earth in terms of familiar objects, that is, in the units of the MKS system. And for that we must know the value of g in the MKS system. The law of universal gravitation implies that the value of g is the same under all conditions. Therefore, if we could measure the gravitational force between two bodies of known mass, separated by a known distance, we could at once determine g, and from that the mass of the Earth. Unfortunately, the force of gravity is just about the weakest known force in nature. It takes a body with the enormous size of the Earth to produce enough gravitational force to bring about an acceleration of 9.8 meters per second squared. The puny forces that could be produced by a few pounds of muscle can and do counter all the gravitational force whenever we chin ourselves, do push-ups, jump upward, or climb a mountain. For bodies that are large, though less massive than the Earth, the decline in gravitational force has drastic effects. The Earth maintains a firm grip on its atmosphere through the force of its gravity, but the planet Mars, which has only 1/10 the Earth's mass, can hold only a thin atmosphere. The Moon has an enormous mass by ordinary standards. Nevertheless, it is only 1/81th. Nevertheless, it is only 1/81th as massive as the Earth, and has a gravitational force too weak to hold any atmosphere at all. Where bodies of ordinary size are concerned, the gravitational forces produced are completely insignificant. The mass in a mountain exerts a gravitational attraction on you, but you are aware of no difficulty in stepping away from such a mountain. The problem, therefore, is how to measure so weak a force as that of gravity. We might speculate on possible ways of measuring the gravitational forces between two neighboring mountains, but the masses of individual mountains are not much easier to determine than the mass of the Earth. Furthermore, the mountains are of irregular shape, and the gravitational force is concentrated at some center, a position that would be difficult to determine. We would therefore have to measure the gravitational forces originating in symmetrical bodies small enough to be handled easily in the laboratory, and the measurement of the tiny gravitational forces to which such bodies would give rise might well be considered too difficult to lie within the realm of the possible. The beginning of a solution to the problem came about, however, in the time of Newton himself, thanks to the work of the English scientist Robert Hooke, 1635 to 1703. As a preliminary to explaining Hooke's work, let us keep in mind that when forces are applied to a body, that body will change its shape as a result. If a plank of wood is suspended across two supports, and someone sits down on the center, the plank will bend under the load. If a rubber band is pulled at both ends in opposite directions, it stretches. If a sponge is clenched in a fist, it compresses. And if rotated at each end in opposite directions, it will twist. If pushed to the right at one end and to the left at the other, without being allowed to rotate, it will shear. All these types of deforming forces can be referred to as stresses. The deformation undergone by the body under stress is a strain. When an object undergoes deformation as the result of a stress, the original shape may be restored when the stress is removed. The wooden plank, after you stand up, unbends. The rubber band, after the pull is released, contracts to its normal size. The sponge, once released from the compressive, twisting, or shearing force, springs back. Again, a steel ball flattens upon striking the ground, a baseball on striking the bat, and a golf ball on striking the club. When the deforming force is gone, all are spheres once more. This tendency to return to the normal shape after deformation under stress is called elasticity. There is a limit to the elasticity of any substance, a point beyond which stress will produce a permanent deformation. For a substance such as wax, this point is easily reached, and even light stresses will cause a lump of wax to change its shape permanently. It is plastic rather than elastic. A wooden plank will break if too great a force is exerted on its unsupported center. A rubber band will snap under too great a pull. A steel ball will be permanently flattened under too great a compression. However, if one works with the forces not strong enough to surpass this limit, one can arrive, as Hooke did, at a useful generalization that can be briefly expressed as follows. The strain is proportional to the stress. This is called Hooke's law. One would expect from Hooke's law that if a force X stretches a spring through a distance y, then a force of 2x will stretch it through a distance of 2y, and a force of x divided by 2 will stretch it through a distance of y divided by 2. Suppose, then, that the amount of stretch produced by a known force is measured. Any force of unknown size within the elastic limit can then be measured by simply measuring the strain it produced. This principle can be applied to any other form of stress that produces an easily measured strain. For instance, it can be applied to the twisting or torsion of an elastic rod or fiber. When torsion is used to measure the size of an unknown stress by the amount of strain produced, the setup is called a torsion balance. If an extremely thin fiber is used, one that can be twisted by very small forces, it becomes conceivable that even tiny gravitational forces may be measured. In 1798, the English scientist Henry Cavendish, 1731 to 1810, made use of a delicate torsion balance for just this purpose. His torsion balance consisted of a light rod suspended at the middle by a delicate wire, approximately a yard long. At each end of the light rod was a lead ball about 2 inches in diameter. Imagine a force applied to each lead ball in opposite directions and at right angles to both the rod and the delicate wire. The wire would twist, and extremely small forces would be sufficient to produce such a twist. As a preparatory step, Cavendish applied tiny forces to determine the amount of twist that would result. Next, carefully shielding his apparatus from air currents, he brought 2 larger lead balls, each about 8 inches in diameter, almost in contact with the small lead balls, but on opposite sides. The gravitational force between the lead balls now produced a twist in the fiber, and from the total angle of twist, Cavendish could measure the strength of the force between the small and large lead ball. It turned out to be about 1/2,000,000th of a Newton. Suppose we rearrange equation 4-1 as follows. Gravity equals force times distance squared divided by the masses of the bodies. Equation 4-2. With the value of F determined, as I have just described, it is a simple matter to measure the mass of the lead balls, m and m-, and the distance between them, d, center to center. Once all the values of the symbols on the right-hand side of the equation are known, it is simple arithmetic to calculate the value of g. Since the units of F in the MKS system are kilogram meters per second squared, those of distance squared are meters squared, and those of m times m- are kilograms times kilograms, or kilograms squared. The units of g work out by equation 4-2 to kilogram meters divided by seconds squared times meters squared divided by kilograms squared, or meters squared divided by kilograms seconds squared. The best modern determination of g gives it a value of 0.0000000000667 meters squared divided by kilograms seconds squared. Certainly a tiny enough value. It is a tribute to Cavendish's great talents as an experiment that in his first determination he obtained a value very close to this. Suppose now we rearrange equation 4-1 as follows. Meters squared equal force times distance squared divided by gravity times mass. Equation 4-3. And try once more to determine the mass of the Earth, m-. We already have in the MKS system a value of 0.98 for force, one of 6,370,000 for distance, and one of 0.1 for mass. If we now add the value of 0.0000000000667 for G, it is simple arithmetic to solve for m hyphen, or the mass of the Earth. You can see that m hyphen is equal to 0.98 times 6,370,000 times 6,370,000 divided by 0.00000000667 times 0.1, or just about 6 septillion kilograms. Physicists customarily express large numbers as powers of 10. Thus, 1,000,000 is usually written as 10 to the power of 6, which signifies the product of 6 tens. The exponent, for numbers larger than 1, signifies the number of zeros in the number. It follows that 6,500,000 is 6.5 times 10 to the power of 6. Negative exponents signify numbers less than 1, so that 10 to the negative power of 6 is equal to 1 times 10 to the power of 6, or 1/1,000,000th, or 0.000001. Again, 0.000000235 is 2.35 times 10 to the negative power of 6. Using such exponential notions, the value of G is 6.67 times 10 to the power of negative 11 meters squared divided by kilograms seconds squared, and the mass of the Earth is 6 times 10 to the 24th power kilograms. In the CGS system, the value of G is 6.67 times 10 to the negative 8 power centimeters squared divided by grams seconds squared, and the mass of the Earth is 6 times 10 to the 27th power grams. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.